Where does life begin? Not among the stars, but right here, on Earth. Billions of galaxies, trillions of planets. The odds that life exists only on Earth seem almost too small to believe. So is Earth a rare exception, or just one of countless worlds quietly nurturing life beneath the surface? This isn't just a scientific question, it's the greatest mystery surrounding our own existence. Scientists believe that only 3 ingredients are needed for life to form: liquid water, organic molecules, and a source of energy. And what's truly astonishing is that all 3 conditions appear to be common across the universe. The Murchison meteorite, which crashed into Australia in 1969, carried over 70 amino acids, the very building blocks of life, suggesting that the seeds of life may not be exclusive to our planet. If microorganisms can survive in volcanic rock buried 3 kilometers beneath the ocean floor, then why couldn't life exist on Europa, Titan, or even Mars? Perhaps we haven't found them yet, not because they don't exist, but because we haven't looked in the right place. Let's explore the first traces of life beyond Earth and seek the answer to humanity's greatest question: are we truly alone in the universe? At its most fundamental level, life is the result of chemical reactions. When 3 essential ingredients, energy, organic molecules, and liquid water, come together under the right conditions, life has the potential to emerge. And if the entire universe operates under the same universal chemical laws as Earth, then perhaps life isn't rare at all. Perhaps it is a natural consequence of the universe's evolution. Across the night sky, astronomers have identified numerous promising planets. Worlds like Kepler-62f, TRAPPIST-1d, and Teegarden b. What they share in common is that they are all rocky planets, located in what scientists call the habitable zone, the sweet spot around a star where liquid water can exist on the surface. Among them, TRAPPIST-1d stands out, one of 7 planets orbiting the ultra-cool dwarf star TRAPPIST-1, with a mass close to Earth's, a temperate climate, and the potential for liquid water, an essential element for life as we know it. According to NASA, this planet offers a promising lead in our search for alien biosphere. But what truly astonishes scientists is the fact that the raw ingredients for life, carbon, hydrogen, and oxygen, aren't limited to just these planets. These fundamental elements have been found in interstellar dust clouds, on the surface of comets, and even within the atmospheres of massive gas giants. These discoveries lead to a poetic but powerful conclusion. The universe doesn't just contain matter, it is quietly sowing the seeds of life. Current statistics suggest that at least 1 in every 4 stars hosts a rocky planet within the habitable zone. In our Milky Way galaxy alone, the number of Earth-like planets may be as high as 50 billion, and when we scale that across the universe, we confront a number almost too large to comprehend: 100 quadrillion planets that may hold the conditions necessary for life. But having the conditions doesn't always mean having life. Not every rocky world is a biological paradise. Venus is a prime example, once believed to be Earth's twin, with similar size, close proximity, and a seemingly stable exterior. Venus quickly turned that hope into a cautionary tale. Its atmosphere contains 96% carbon dioxide, and an extreme greenhouse effect pushes surface temperatures above 860 DE feet, 460 DDE feet hotter than even Mercury, the planet closest to the Sun. This harsh truth was confirmed by the Soviet Venera program. Among them, Venera 13, which reached Venus in 1982, lasted just 127 minutes before it was destroyed by the planet's intense heat. These facts lead us back to a deeper question. If ideal living conditions could exist on hundreds of trillions of worlds, how many of them can truly be called home? The question is no longer, does life exist beyond Earth, but rather, among 100 quadrillion potentially habitable planets, how many actually host life? How many are not just habitable but inhabited? To find the answer, scientists have pushed their vision beyond traditional habitable zones, those regions where water can exist as a liquid under the warmth of a parent star, because perhaps life doesn't need sunlight at all. Take Enceladus, one of Saturn's frozen moons. Data from the Cassini probe revealed towering plumes of water vapor erupting from a vast subsurface ocean beneath its icy crust, carrying hydrogen, methane, and complex organic compounds, chemical ingredients essential for life. This activity isn't powered by sunlight, but by tidal friction, generated from the gravitational pull between Enceladus and Saturn. Farther out lies Titan, Saturn's largest moon, where vast lakes of liquid methane and ethane stretch across an alien, freezing landscape. With average temperatures around -290 DE5, 179 DC, scientists now ask a bold question. Could there be a form of life completely unlike our own, built not on carbon, but on silicon? A life form that operates unimaginably slowly, adapted to extreme chemistry we have yet to understand. And it doesn't stop there. Astronomers have discovered the existence of rogue planets, worlds drifting through the endless dark, unattached to any star, with no day, no night, only eternal shadow. And yet, some of these planets may still retain internal heat, powered by radioactive decay in their cores or gravitational interactions with companion moons, providing enough energy to maintain stable chemical environments for extended periods of time. All of this is forcing us to redefine what it means to be habitable. If life can exist without sunlight, without a familiar atmosphere, without even a star, then perhaps the universe is not as lifeless as it appears. Perhaps life already exists in the ice, in the dark, in the chemistry we haven't yet understood. And if that's true, then maybe the universe isn't lacking life. Maybe we just haven't learned how to see it yet. If life isn't a cosmic anomaly unique to Earth, then the greatest question we face is no longer, are we alone? What does life out there actually look like? In this universe, there is no room for pure chance. Every form of life, whether floating in the hydrogen-rich skies of a gas giant or hiding beneath thick layers of ice on a distant moon, must obey the unchanging laws of the cosmos. Gravity, pressure, thermodynamics, molecular structure. These are the molds from which life is cast, wherever it dares to appear. And when these fundamental elements come together, something extraordinary can happen. Carbon, the sixth element with its extraordinary bonding ability, becomes the backbone of biology. It not only forms proteins and DNA, but also has the potential to organize itself into self-sustaining chemical chains, what we call life. Whether life emerges here on Earth or millions of light years away, it must still arise from the same periodic table and the same universal physics. And if that's the case, then alien life, no matter how foreign, may turn out to be strangely familiar. here on Earth. Eyes have evolved independently more than 50 times, from primitive light sensors in crustaceans to complex visual systems in mollusks. So it stands to reason that on a distant planet, facing darkness, distance, and challenge, another species could invent eyes of its own. And not just eyes. Flight, echolocation, communication through light, all are tools of adaptation that could be reinvented on any world facing similar pressures. Even alien plants may operate under this same logic. If their star emits weaker light than our sun, their leaves may appear jet black, optimized to absorb longer wavelengths. Imagine glowing purple fields, crimson forests, or grasslands that shine softly at night. Entire alien ecosystems that follow different rules but familiar patterns. Then a quiet realization begins to emerge. We might recognize alien life, not because it's completely different, but because within the unfamiliar, there is something deeply familiar. Perhaps deep within the DNA of the cosmos, where the first ancient reactions began, life has always known how to reflect itself, adapting into endless forms wherever the universe allows it to take root. But not all life would resemble us. Some scientists believe that life could be built on a silicon-based framework rather than carbon. Silicon is capable of forming complex molecular structures, and in extreme environments like the methane lakes of Titan or the molten cores of rocky planets, silicon-based organisms might emerge. They could evolve slowly with metabolisms that span centuries. They might not breathe like we do, move like we do, or think like we do. Instead, they could exist as waves of chemical reactions, drifting through strange fluids, or lying dormant for millennia beneath layers of magma. To us, they might appear as stone, but to themselves, they are alive. Among billions of potentially habitable planets, could one of them have gone beyond the microbial stage and reached the heights of intelligence? So what happens if, after centuries of searching, humanity still hears nothing? No reply, no signal from the other side of the galaxy. In that silence, one possibility begins to emerge. We might be the first. And if that's true, then we are not just seekers, we are the keepers of the universe's first spark of life. Entrusted with a responsibility far greater than ourselves, to preserve life, to spread knowledge, and to become the torchbearers of the cosmos. If no one else is out there, then are we ready to become the giants? So far, no one has answered, not a single clear signal. We've scanned millions of frequencies, sent messages carrying the name of humankind, but no one has replied. Each passing year, the chances of meeting alien life grow smaller. Planets die, stars age, the universe continues to expand, and the silence deepens. And yet, amid that silence, one thing still burns: curiosity. It was curiosity that led a fragile species to stand upright, to look skyward and set foot on the moon. It launched probes beyond the edge of the solar system. And it continues to push us to write equations, send signals, and search for a sibling we've never met, somewhere beyond the stars.